let's say a charge equal to 2 microcoulomb has a velocity, some random velocity. So let's say the velocity is negative 2i plus 6j plus 3k, and the magnetic field is equal to 6i minus 2j plus k. Let's say millitesla, since a Tesla is very strong. Okay, something like that. And let's say the original position of the charge, is 135 meters. So it looks something like this: X, Y, Z. Okay, so we have the charge enters this field, and you get here 1, 3, 1, 2, 3, 4, 5. So something like this. That's where the charge is, right? And then the velocity of the charge is -2. So that means it's going to the left, right, in the x direction. -2, 6, and then 3. So -2, 6, and then 3 this way. So it's kind of like this. So it's going to the left, up, and out of the board in some random velocity. Okay, and then the magnetic field looks like what? 6. So the magnetic field is going to the right, 6, -2, and then 1 this way. So something like this. Like this, like this, like this. So then what's going to happen to that charge? It looks like this angle between them. See, the magnetic field and the velocity vector make a plane, a three-dimensional, in the three-dimensional field, right, make a plane. So we can find out first the angle between them. So we could say, what is the angle between V and B? To do that, you do the dot product. Cosine theta is V dotted into B over magnitude V, magnitude B. So the dot product is the quickest way to find the angle. It looks like it's probably an obtuse angle, greater than 90. So the dot product is going to give you -12, another -12, plus 3 over magnitude of V. Magnitude of V is going to be 4 plus 36 plus 9 square root. And then square root of 36 plus 4 plus 1. So already we can tell that it is an obtuse angle. When the dot product is negative, that means cosine of theta is negative, and cosine is only negative in the second quadrant. So it is an obtuse angle. So this is going to be negative 24 plus 3 is negative 21 divided by, this is going to be square root of 45, 49, right? So 45, yeah, 49. And then this is square root of 41. Oh, this square root of 49 is actually 7. That's good. So negative 21 divided by 7. So divided by 7. Okay, negative 3. Right, divided by 41 radical. Okay, then I'm going to take the cosine inverse of that. Second function, cosine inverse, 117 degrees. 117.938 degrees. Okay. The next thing to do would be to break up the velocity into parallel component and perpendicular component. So remember yesterday we saw only the perpendicular component of V to the magnetic field gets affected by the magnetic field. So we can kind of break the B field into like this, kind of like that. You see? Make a line and then break this V into like this. B parallel, which is anti-parallel, but that's the same thing, it's okay. And then this is V perpendicular. V perpendicular. You see, so then V parallel is going to be V times cosine of theta. So cosine theta. So then it's just going to be the magnitude of this square root of 4 plus 36 plus 9 times cosine of 117.938. So it just means it's the negative. Well, negative means that the parallel, the projection of V onto B is negative, means that it's 180 degrees from the magnetic field, you see. And so then we take 117, we take cosine of that times, and then this is 49 square root, oh, so that's the 7. So the magnitude of the velocity vector is 7. So cosine times 7. Okay, so that's negative 3.2796 meters per second. So that's the parallel component. And then the perpendicular is going to be V sine of theta. So it's going to be 7 sine of 117. .938 sine times 7. 6.1842 meters per second. Also, it's not actually as big as I made it out to look. Mine looks like it's more like close to 180. So the perpendicular is actually bigger. Okay, so then what's going to happen to that? The perpendicular, we could say V is this way. The V perpendicular is like this, kind of coming out of the board. V perpendicular like this. So it's going to experience a force like that. So the charge is going to go like this, then like that, and like that. I'm trying to visualize the path that it's going to make. So in the initial force pushes it out that way. And then it goes that way, then it turns, then it goes like that, a corkscrew. And then it goes like that, like that. So it goes basically along the direction of the B, but opposite to the direction of the B. Because remember, the parallel component of the V is unaffected by the B. Okay, like that. So then we can ask, what is the radius of that orbit? What is the radius? What is r? And what is the pitch? Remember, the pitch was the distance between this, the distance between each one. And then the radius, what is the pitch? And then what is the period of the orbit? What is period? Okay, the period is how many seconds it takes for one turn, like this, and then come back. You see. So then the radius of the orbit, remember, it's going to be F is equal to mv perpendicular squared over r. So only the perpendicular component takes part in the circular motion. So the radius of the orbit is mv perpendicular squared over f. So that's the magnitude of the force. Let's see, mv perpendicular squared over the f. And then f, the magnitude of the force is going to be qv crossed into b. For our purposes, we just need to know the magnitude of the force for now. So the magnitude of the force is qvb sine theta. Right, so qvb sine theta. So if I put the magnitude of the force here, mv perpendicular squared over qvb sine theta. Okay, so then we're going to say, well, v sine theta is v perpendicular, you see. So we have here qvb sine theta, v, this is v perpendicular, so we have here mv perpendicular squared over qv v perpendicular. So then this cancels. So I just need to put v perpendicular at the top. So that kind of is similar to the radius equation that we had yesterday. R is mv over qb. So it's the same thing that we had, but except here, v, we don't put the total v. We just put the perpendicular component of v to the magnetic field. So it's the 6.184. Okay, so then the radius of the motion is going to be the mass. What did we give it the mass? Okay, let's say the mass was 100 grams. We had already said the charge is 2 microcoulomb. So let's see what that's going to give us. If the mass is 100 grams, that would be 0.1 kilogram. V perpendicular would be 6.1842. This is 2 microcoulomb. And then the magnetic field is, let's see here. It's this guy, right? Oh, but it's a millitesla. So it's a millitesla. Oh, you know what? Let's make it a microtesla. Otherwise, so that'll be more similar to Earth's magnetic field, a microtesla. Otherwise, the radius is going to be so huge, right? So we'll make it a microtesla. Okay, so, oh no, that's even worse. What am I saying? We want it to be, oh, okay, no, it doesn't matter what, no matter what I do, the radius is going to be huge. Okay, let's go back to millitesla. Okay, so now we have 0.1, 6.184, charges 2 times 10 to the minus 6, and then B is, so square root of 41. and then the millitesla. So then it'll be 10 to the minus 3. Oh, wow, the radius is huge. So in other words, everything that I had about this problem is lends to a huge radius. So it's going to be, wow, like this, you know, very, very large radius. So if the B field is small, it tends to take a long time for it to turn around, you know, to make a radius. And if the charge is small, that also produces a large radius. And if the velocity, the only way to say, oh, let's get like no more normal radiuses is to make the mass very, very, very light, right? And also the velocity very, very, very small. So that's kind of how it works out. You want to make this small to make the radius small, and then you want to make that big. Otherwise, it comes out huge. Okay, so let's see what this comes out. 0.1 times 6.1842 divided by 2 divided by 41 square root. Okay, 0.04829 times 10 to the 9th. So 48.29 times 10 to the 6th meters. Wow, it's huge radius. Okay, cool. And from there, then the period is probably the better thing to calculate first. The period is 2 pi r over the velocity perpendicular. So it tells you that how long it takes for one revolution. So then 2 pi, the period is also going to be very long. 48.29 times 10 to the 6th over the v perpendicular, which is 6.1842. So this is times 10 to the power 6. No, hold on, I did something. It's times 1,000. Yeah, it's 48,290,488 seconds. No, that's meters. Then times 2 times pi divided by 6.1842. So that's seconds. 49. You can say 0.063 times 10 to the 6 seconds. Yeah, you're doing 2 pi times that.
Is it the 7th power? Oh no, it's 6.
Yeah, it's 6. Yeah, 49. I'm making it times 10 to the 6 so we could also write megaseconds, megameters. Right, so for short. And lastly, the pitch would be V parallel times the period. In other words, how long it's traveled during one time that it's gone around, right? During one time that it's gone around, how far it's traveled this way. Then one more time, how far it's traveled that way, so on, like that. Okay, so then you just do V parallel times the period. So the V parallel would be the 3.2796 times the period 3.2796. Megameters. So this is kind of the thing that would happen, as I was saying yesterday, from the solar wind. Let's say if this is the sun, these charged particles come. So let's say during the summer, when the Earth is facing the sun, June, right? And then you've got the magnetic field of the Earth is like this. You see, so this, if you go detail of what's happening, so let's say one charge is coming here, you see, and then this charge is coming here. So zoom in on what's happening in that area, right? Zoom in on this and say, okay, what's happening here? Try to blow that up. So here you have a field going like that, you see, and then you have an incoming charge going like that, you see. So it's kind of similar to what we have in this problem. You've got the B field going this way, you got V going this way, and let's say the charge is positive, Q this way, right? So then you got, this is the V parallel, and this is V perpendicular. You see? So then what's going to happen? Due to the perpendicular, you do the cross product, V perpendicular crossed into B out of the board. So this charge, as soon as it enters the magnetic field of the Earth, it's going to come out of the board and go in and like this. But then the V parallel is unaffected. So then this one will come like this, like this, like this, you see. Out of the board, into the board, go like that. But now as you're going this way, what's happening? The field is getting stronger. Remember, it goes from 0.25 microtesla to, 0.25 Gauss to all the way to 0.65 Gauss over here. So what does that do when you get to a stronger B field? When the B field gets stronger, the radius gets smaller. And if the radius gets smaller, the period gets smaller. And if the period gets smaller, the pitch gets smaller. So this is what happens. This is like as detailed as we can see it. Here's the field. So out of the board, into the board, out of the board, into the board, out of the board, into the board. You see the radius is getting smaller now. And as the radius gets smaller, the pitch gets smaller. And the period gets shorter. In other words, it goes around quicker. Something like that, let's see. And that blast of the solar wind is likely to cause aurora in the southern hemisphere. You see? So it goes like this. It almost looks like a tornado, doesn't it? Yeah, I just thought of it. So the pitch, the distance between them is getting shorter, 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 shorter. You see? So it's going to give you, it's almost like it goes through like a freeway, kind of like a bottleneck, right? It goes through a bottleneck, and then a bunch of charges are coming in like that, all to bottleneck, and that energy is released. Any questions on that? So you can kind of see this scenario is happening. So I guess you can say during the summer months, we're more likely to get auroras in the southern hemisphere because most of these charges are going to come. Only the ones that are on the top portion are going to go towards the north. It seems like that. Let me see. Let me see if my hunch is right. Although the environment is far too harsh for permanent human residents, many cruise ships choose to stop here during summer months. When the weather warms up, around 2,000 people populate the island. Basic facilities are made available. Southern Lights, Aurora Australis. Northern Lights happen in summer. While technically northern lights are present for much of the year, there aren't enough hours of darkness to see them during the summer months. Even above the Arctic Circle, the aurora is its most active around the equinoxes in March. Okay, so I guess aurora is the best time to see it in the northern is March and September. In Arctic Circle, they are known as aurora borealis or the northern lights, while in the Antarctic Circle, they are called aurora australis or the southern lights. Okay, any questions on that? So I think it might be true that in the southern, in the summer, they're more prevalent in the southern hemisphere, because since the Earth is tilted like this, more of them come at an angle such that they're going anti-parallel to the Earth's field, you see. In order for them to go the other direction, it would have to look like this. The field would have to be going like this, like way over here, and the charge would have to be coming like this. And let's say this is the B field, and then this is the perpendicular component, and this is the parallel component. You see, so in order for the charges to go this way, they come in like that, and then you break, this is the B field, and then if this is their V, this is the perpendicular component. So in order for the parallel component to be parallel to the B, it would have to be the solar wind particles that are coming way over here to the northern section, and then they can go that direction. But then the other problem is during summer months, the northern hemisphere gets mostly sunlight, so it's hard to see aurora. So you've got two issues going on, and that's why the website said it's hard to see aurora here in the summer months because of the daylight. Then opposite is true in the winter. So if you got like that, now most of the ones are charges that come in are more likely to go this way. You see, so I would say probably December is much better to go to the northern hemisphere to see aurora, and then in summer it's better to go to the southern hemisphere to see aurora. Okay, now let's cover the magnetic force on current carrying wires and rods.